Chapter 7, Section 5, is talking about different types of chemical reactions. And in this section, our learning goal is to identify the reaction as a combination, a decomposition, a single replacement, a double replacement, or a combustion. And there are certain things to look for. So it's pretty straightforward once you know what to look for. So hopefully you'll learn that in this section. Now then, you will notice here's our types of reactions that we just talked about, what I wanted your goal to learn in this section. The combination, the decomposition, single replacement, double replacement, and combustion. So let's talk about combination. Think about what the word actually means. You're going to combine things. So in a combination reaction, two or more elements form one product. So we can either have simple compounds combined to form one product, whether it's just an element, and like magnesium plus oxygen gives us magnesium oxide, or if it's two compounds to give us one bigger compound. Notice we have two or more reactants combined to yield a single product. Combination. It actually makes sense. So here's a visual example of combination reaction of burning some magnesium ribbon in oxygen, forms a white powder. Magnesium oxide gives off this brilliant light. It's kind of a neat reaction to watch. Now a decomposition reaction is just the opposite. You have one substance that splits into two or more products. So notice it's just the opposite, and it's decomposition, which if you think about the word decomposition makes sense. So we have, for example, our one reactant splitting into two products. One reactant splitting into two products. Decomposition. And here's a visual item. Now notice we have our, actually a compound, and we have our, that's breaking into the two elements. Excuse me. Now, in a single replacement, let's think about what those words mean. Replacing, and then single. Just one element is going to go in and replace another element in a compound. So the visualization would be like A is going to go into BC, kick out B, and then we have the compound now AC. And you may go, well, why didn't it go out and kick out C? Well, it actually depends on what this one element is. If this one element is a metal, then it goes in and kicks out the metal of the compound. And remember, the metal is always written first. So here we have this zinc. Zinc goes into HCl. And you go, hydrogen's not a metal. Well, I know, that's like always the one exception, but it is on the left-hand side of the periodic table, and it's quite often written as a positive. So this zinc can go in there, because when it becomes an ion, it becomes positive. So it can go in there and kick out this positive and hydrogen, and zinc is going to hook up with the chlorine. Now when it does, you can't just throw out all of your learning about compounds. You will notice that we have our zinc chloride hooking up the way you would expect it, because zinc is a +2, our chloride ion is a -1, and hydrogen is a diatomic element. And so that means if hydrogen is all by itself, then it's not all by itself. It's going to hook up with another hydrogen. So hence the word, hence why H2. But I want us to make sure that we look at this single replacement reaction and notice we have one item going in and kicking out the other item. So here we have our iron. It's a metal, so it's going to go in and kick out the item that's in front, which is the copper. And when copper comes out, copper is not diatomic, copper is this, and we have our iron 2 sulfate. But in this section, I'm just trying to have you predict what type of reaction it is. So this is an example of a single replacement reaction. So here's our visualization. We have our zinc, which is fairly reactive, you put it in some hydrochloric acid, pretty soon you see some bubbles forming. And what are those bubbles? But those bubbles that are forming the hydrogen gas. And the solution then is our zinc chloride. Now in a double replacement reaction, the positive ions in the reactant compounds switch places. So in a double replacement reaction, we have two ionic compounds here, and our A is going to hook up with our D, and our C hooks up with our B. And you go, well, why do you have CB and not BC over here on the products? Well, because C is the positive side, so it always goes first, and that's why C over here is written as CB. Now, you will notice that A goes in, kicks out C, A hooks up with D, and then C hooks up with B. So it is being replaced, but two of them are doing the replacement. So we have our silver nitrate plus sodium chloride. When the silver goes in, kicks out the sodium, our silver hooks up with the chloride, and our sodium hooks up, the sodium and the nitrate is written this way. Now in our zinc sulfide plus hydrochloric acid, the zinc goes in and kicks out the H. Now then, our H is going to hook up with our sulfur, H2S, hydrogen sulfide, and zinc chloride. So you will notice there's a double replacement. They switch places, hence double replacement. And so here's a visualization. Now in combustion reaction, think of fire. Now let's see what you need for fire. First of all, we need oxygen. And then what are two products of a fire? Well, two products of a fire, when we're talking about a carbon-containing compound, then two products of fire always. One of them is carbon dioxide and one is water. Of course, energy is also released, and so technically that's a product, but if we're talking about the compounds are CO2 and water. So when you're looking for a combustion reaction, let me point out what you always have to have. So besides the fuel, you have to have oxygen, because oxygen is required for a fire, and the two products, which you know, with the forest fires going, or the forest fires in the Amazon going, one of the issues is CO2 gas. Well, we have CO2 and water vapor that's actually produced with a fire plus energy. But so this is what you look for. So here we have our methane. Our methane plus oxygen gives us CO2 and water. Here's our propane. We might have a propane tank out back. Propane and oxygen gives us CO2 and water. Combustion reaction. That's what you look for. Now, you don't always have a perfect fire, and sometimes you have an incomplete combustion, and a little bit of smoke comes out, like the exhaust or whatever, and that's carbon monoxide. And so this is not a perfect reaction, certainly with burning, but that is actually another product. And an issue with that is that because it's colorless and odorless, we don't always know what's happening. And it attaches to the hemoglobin molecules when inhaled. And when it does, it makes it then that those hemoglobin molecules can't then absorb the oxygen gas. And so then the oxygen can't reach our cells, and then we are going to experience a reduction in exercise capability, visual perception, manual dexterity, and possibly death. Sometimes if you're going out boating on Lake Powell or boating somewhere and you're behind a houseboat and you're back there where the engine is, you don't even know you're exposed to the carbon monoxide, and you, if you're back there trying to swim around near it, and you have issues. And that's an important thing to make sure you're not near. So here's a little bit more about this. So hemoglobin is a protein in the blood that transports oxygen to the cell. When the hemoglobin is bound to the carbon monoxide, which is the bad stuff, the incomplete combustion, it When it reaches 10%, a person may experience shortness of breath, headache, drowsiness. So if you start feeling that, get the heck out of wherever you're at. At 30%, a person may experience more severe symptoms, dizziness, mental confusion, severe headache, and nausea. At 50%, a person could become unconscious and die if not treated immediately with oxygen. So here's a summary of the different reaction types that you can go back and look at Table 7.4 if you need. So here we go. Here's our learning check. Please identify each of these as a combination, decomposition, combustion, replacement, or double replacement. Well, let's look at this. We have one item plus a compound, and then our products, it looks like our aluminum goes in and kicks out the hydrogen because our aluminum is now hooked up with our sulfate and out pops hydrogen. Well, that is a single replacement. All right, B. We have a compound and we have a compound, and notice the compound, the sodium hooks up with the nitrate and the silver hooks up with the sulfate. So obviously there are two items there switching places, double replacement. Now here we have our carbon and we have our rust, our iron 3 oxide. And when we see here, our carbon goes in and kicks out the first item. And so this is an example of a replacement reaction. However, it is only one item, a single replacement. Now on D, we look here to see what's going on. Oh, we have oxygen as a reactant and we have CO2 and water as products. And we have some carbon compound at the beginning. That's a clue. That is combustion because we have oxygen as a reactant and two of the products, CO2 and water. So let's look and see what they say. Yep, they have this solution, single replacement, double replacement, combination, and then we have our combustion. Let's look and see back there. Wow, that's weird. That's different, okay, than what we had there. So let's take, for example, if we did have this, if we had our N plus our O2, we would get our combination. Now, hopefully we don't have anything sneaky like that for our next one. This is our last one. Please press pause and come back. So as you look at this, we have two items that make one, so that is a combination. On this one, we have the element, and we have a compound, and we see that the element switches places with the first one, and so we're going to have a single replacement. This one we have a carbon compound, we have oxygen as a reactant, could be a fire, and we look to see, oh yes, we have CO2 and water as a product, absolutely, it's combustion. Here we have a compound, and notice that the elements, the metals switch places. So our potassium is going to hook up with our chloride, and our lead hooks up with the sulfate. So that is a double replacement. Notice here we have one item and it breaks down into two or more items, so that is a decomposition. So as you look at this, this is exactly what we just mentioned.